Okay, we're on lesson 7.2, Anti-Differentiation by Substitution. Some textbooks calls this U substitution, and I think that's our textbook's way of talking about it as well. But the title is just says substitution, so you just kind of have to get used to it. So another way to look at this is looking at chain rule backwards. So, to make sure you understand, in order to really fully utilize this method, you have to be good at chain rule to begin with. So knowing your derivatives from last semester is very, very important. You might want to go back and revisit that lesson. I believe it's either it's in the beginning of chapter 4. So you want to check your, I think 4.1 or 4.2 notes for this. Okay. All right. So in the beginning, in the first two problems, I'm going to give you what the U variable is. So there's 3 steps to these type of problems. Step 1, set up a U. Step 2, take the derivative. Step 3, you move the coefficient. And you're going to see me do that over and over again in these problems. So the most important thing, the very first thing you want to do is set up your U. So in the first two problems, we have the training wheels for you. We tell you what the U is. So number 1, I tell you that U is set up as 2x squared. So U is 2x squared. Now I'm going to use green to kind of show you how the substitution happens, and I strongly recommend that you maybe use some color coding on your notes so it's easier for you to see how the replacement happened. So this is called U substitution because we're replacing some of the terms in this integral, so it's actually doable. Right now in this original integral, you have product rule here. You have x times cosine of 2x squared. You have 2 x's here. You're really multiplying these two together, so it's really not straightforward. You can't really take the antiderivative. So we're going to make it so it's actually doable. So step 1, set up U. Step 2, take the derivative. So du equals 4x dx, right? In the past, we had u prime, but you don't want to write u prime because that's a little too messy. It's du over dx, so I did the separation of variables and move the dx over to the right-hand side so that the x's are staying together. So that was your step 2. Step 3, coefficient. Move your coefficient. Your coefficient's a 4, not the whole x term, just the 4. So you move it over by doing algebra. You can divide 4 over, or you can multiply both sides by 1/4 so that it becomes like this. Okay, so now I'm ready. That was step 1, 2, and 3. So what am I going to do? I'm going to go ahead and look at my original function here. If you can see, your x dx gets replaced right here, right? Your 2x squared got replaced right here. So the only thing left of your integral was the cosine. So cosine didn't move, right? Cosine of, now this is your u, right? So that got taken care of. And then the x dx gets replaced by 1/4 du. Be in a good habit of moving your coefficient outside because then it makes your integral a little bit easier and quicker to work on. Okay, now look at your new integral. This new integral, first of all, is definitely much more doable. It's just cosine of u. You can take the antiderivative of cosine. Secondly, it is in terms of u. There's no x and u. When you do u substitution successfully, you will see that your variable is just now down to 1, just u, okay? All right, so now I can take the antiderivative, 1/4 out here. The integral of cosine u is sine u plus c. So one more thing, you don't want to leave it as u because that was a substitution you did. So put back your u, which was 2x squared, into your equation. And there's your final answer. That's your equation. Now, because this is notes and because this is the beginning of you looking at U substitution, it says to check by confirm your answer by differentiation. So what I'm going to do is I'm going to take d dx derivative of this equation I got down there, 1/4 sine of 2x squared plus c. Okay. When you're taking derivative, the coefficient stays, so 1/4. This is what I'm talking about, chain rule. You have to know your chain rule. Chain rule says take the derivative of sine, that would be cosine of 2x squared. You leave the inside the same. Then the next piece is 2x squared. You multiply by 4x. And then the c is a constant, so 0 and it's gone. You reduce out the 1/4 and the 4. You clean up. So you have x cosine of 2x squared. And that was my original antiderivative integral here, right? So this is how it works. But in order to make your check work for you, you have to know your chain rule, okay? All right. Number 2, start off the same way. You have your training wheel here. It tells you that u is 1 minus r cubed. So step 1 is already done for you. U equals 1 minus r cubed. So now let's take the derivative. Du is negative 3r squared dr, right? Move the coefficient. negative 1/3 du equals r squared dr. Okay, now I'm ready to go ahead and substitute. Now this 9 is a coefficient. I'm gonna move that outside so it's a little bit more doable. You can always move your number outside, okay? Notice your numerator r squared dr now gets replaced by negative 1/3 du, right? The negative 1/3 goes outside as well with a 9. And then your bottom is u, and then there's a square root there, right? Again, this equation now, this integral is definitely doable, better than the one before. The one before had quotient and there's some chain involved, so this is a lot easier to work on. I'm going to do two things before I start my antiderivative. I'm going to clean up the 9 and the 3, and I'm going to rewrite this as a power so I can take the antiderivative. So negative 3 integral u to the negative 1/2 du, right? Okay, now I can take the antiderivative. I get negative 3 u to negative 1/2. Yeah, add 1 to your exponent, so it's becomes positive 1/2. Divide by 1/2, so multiply by reciprocal, so multiply by 2 plus c. So my final answer is negative 6 square root of whatever u was 1 minus r cubed. As an equation, rewriting it back to the square root is a lot more handy and a lot more useful. As a derivative, you want to keep it as a 1/2 because that's actually a lot more easier to tackle than the square root, okay? So this was your final answer as my equation. And again, this is notes. It wants you to check by taking a derivative. So I'm going to check by taking dr of negative 6, 1 minus r cubed to the 1/2 power plus c, right? So now I'm taking a derivative. I'm going to leave it back as a 1/2 power, so it's a lot easier to take the derivative, right? So chain rule says coefficient, negative 6 stays here. Take the derivative of the outside, so 1/2. 1 minus r cubed to the negative 1/2. Now the inside piece, the derivative is negative 3r squared. I'm going to clean this up. Negative 6 times 1/2 is negative 3. Times the negative 3 is positive 9, r squared. And then since this is negative 1/2, it goes downstairs. 1 minus r cubed. And again, notice this is my integral to begin with. Okay, now the training wheel is off. Number 3, 4, 5, and if you look onto your notes, you don't see what the u is. So you now have to figure out what the u is, because that will be step 1. That's the most important step, right? Figure out what you should set up as your u, and then you can figure out the rest of the steps with taking a derivative and then moving the coefficient. So a few things here, let's just find a spot to take notes of. So here are the few suggestions, right? So typically we take what's inside the parentheses or what's inside my square root as a u. That would be set up as your u, okay? Another typical situation is when you have a fraction, you have a numerator over the denominator. Usually the denominator is your u, okay? Another one is when you have two different powers. So this is like negative 3/2 power and this is like squared, for example. You want the one that's a more complicated power. May not be the biggest, but you want the one that's more complicated, and that will be set up as your u. If you have an equation of e to something, that exponent is your u. Last but not least, if your equation has natural log anywhere, natural log of x over x. Now I know, Ms. Chu, there's a denominator there. No, when you have natural log of x, natural log is your u. So natural log kind of trumps everything, all right? So these are kind of your 5 different situations, and it pretty much covers everything you will be able to see, okay? So with that idea, let's take a look at what I have here. This equation is a little bit harder to see because the square, when you are taking a trig function to a power, it usually is a little bit more confusing for students because the power is in the middle. So I usually tell them to just kind of rewrite it so we can see it better. This is really tangent of x squared, secant of x squared dx, right? So my suggestion that I just gave you now doesn't work very well because both of these are in parentheses and both of these are to the same power. So it's a little harder to see which one to set up as your u. So let's take a look. You have your options, right? You have 2 options. You either set it up as tangent x or you set it up as secant x. Which one is better? If you say u is tangent x, then du, what's the derivative is tangent, secant square x dx. So in this case, I can see this is really u squared, and this is du. Everything got taken care of. What if you do the other one? Okay, what if I did u is secant x, and then derivative will be secant tangent, right? So that means then, in this equation up here, my equation had tangent x tangent x, secant x, secant x, right? Because it's tangent x squared, secant x squared. So if I set up the first one as your u, these two together is my du. Notice I have a leftover here. I can't have my equation having u and du. That's how you know when you're doing your u substitution. If your substitution is not making your equation easier, then that's not the way to go. And so this is not the setup we want to go, but instead setting up u as tangent x. Okay, so go ahead and set up u as your tangent x. And now sometimes step 3 is moot, because if I don't have a coefficient, or really my coefficient is 1, then I don't really need to do step 3. All right, so now in this case, my integral gets replaced beautifully. It goes integral u squared du. And notice I didn't put my interval in. I didn't put anything here and here, because those numbers, the negative pi over 4 and pi over 4, they pertain to my x. They don't go with a u. So I'm not going to put those down because they're not my numbers to plug in. I'm going to go ahead and work this out and say, okay, well, this antiderivative is u cubed over 3, right? And I have an interval, but I'm not putting it in yet because those numbers are for my x's. So I'm going to take one more step, put my x back in, so I can plug in negative pi over 4 and pi over 4. So my x was tangent of x. Okay. Now I can do this. Now I can do my normal integral and plug it in. Plug in the b and then plug in the a and subtract. So you have tangent of pi over 4 cubed over 3 minus tangent of negative pi over 4 cubed over 3. Right, tangent of pi over 4 is 1. So you get 1 cubed is 1/3 minus negative 1/3, which gives me a final answer of 2/3. Very nice answer. Okay. All right. Following the same steps, following the same suggestion I gave you. So we take a look at number 4. What's in the denominator and in parentheses is just the 2 plus sine t, not with a square. So if I set up my u as 2 plus sine t, okay, now take the derivative. du is cosine t dt. Okay, now I don't have a coefficient, so I don't have to move that. So step 3 is moot for me. Okay, now I can go ahead and substitute. The 6 is a coefficient. I'm going to put the 6 outside, right? And then the top, the cosine t dt gets replaced by du. 2 plus sine t gets replaced by u. Okay, this is definitely clean and doable. So this becomes 6 integral u to negative 2 du, right? Any power that is not a negative 1 power, you can use power rule. It's only when u is u or x is to negative 1 power, then you have to use natural log. Okay, so let's take the antiderivative. I get u to negative 1 over negative 1 plus c. I clean this up. Negative 6 over something to the 1 power plus c. I'm going to put the u back in. The u was 2 plus sine t. And that is my final answer, right? This one doesn't have an interval, so I don't have to do more with it. If you recall, we had a table of our antiderivatives. And if you remember, we had antiderivative cosine and antiderivative sine, but then there's no single cosecant or single cotangent or single secant or tangent, right? So when you're dealing with a cosecant, they gave you a really interesting hint. You're going to multiply this integrand, this equation here, by this much bigger fraction. And it's going to look worse at first, but it's actually going to clean up really nicely. Okay, so I'm going to take that advice and say, all right, my new integral is going to be this multiplied by this fraction. So really, you're multiplying this to the numerator. So you get cosecant square x plus cosecant x cotangent x all over cosecant x plus cotangent x, and don't forget your dx. Okay. All right, so now I have this lovely bigger fraction, and I have a fraction. So my hint to myself was set the denominator as my u. U is cosecant x plus cotangent x. If I take the derivative cosecant is negative cosecant x cotangent x. The derivative cotangent is negative cosecant square x, don't forget your dx. If I divide everybody by, or if I multiply everybody by a negative, because really the negative on the right-hand side is a coefficient. So I'm going to move that over. So negative du makes this positive cosecant cotangent x plus cosecant square x dx. Now take a look at this. Isn't this the same thing as this numerator? So this u substitution works really nicely. It becomes negative, and you have du over u. Okay. This is what we were talking about. Your denominator, this u, is really to a -1 power. So when you have du over u, or u to the 1 power in the denominator, this becomes natural log. So this becomes negative natural log of u plus c. So the final answer would be negative absolute value, because anything in the natural log needs to be absolute value, cosecant x plus cotangent x plus c. And that would be your final answer. Okay, so with number 6, notice it says, hey, it has another set of directions here. It says, make a u substitution and integrate from u of a to u of b. If you recall number 3 here, we had to use u substitution, but then we had to change my equation back to the x. Then I was able to plug in the a and the b. To me, that's a little bit more work, right? That's more work than I really want to. Could you have changed these numbers so that it goes with the u, and then I don't have to change anything back? I just continue working with the u and plug it in at this point right here, and that way I don't have to switch back and forth. Yes, the answer is yes, right? So we're going to start the same way. Set up your u. So in this case, u would be 4 plus r squared, because that's in my denominator and in parentheses. Du is 2r dr, move your coefficient, 1/2 du equals r dr. Okay, new thing. You want to plug in your a and b into this equation here, into the r here, so that it becomes something that's u, right? So I typically plug it in the way it is situated. So I plug in the b first because it's on the top, and I plug in the a because it's on the bottom. That way I don't mess up my order, right? So u of 1 is 4 plus 1 squared, that's 5. U of -1 equals 4 plus -1 squared, that's also equal to 5. So you may notice something at this point, but let's continue with the substitution, right? So if I substitute this, this 5 is a coefficient. I'm going to put the 5 outside. Okay, the bottom is something squared. The top was r dr, r dr. R dr gets replaced by 1/2 du. The bottom was u squared. And my interval, the 1 got replaced by the 5. -1 also got replaced by the 5. And at this point, you can tell yourself, hey, my interval is going from 5 to 5, 0. There's no area at all, right? So this u substitution made your equation much easier to do. In fact, you actually don't have to do more work because you knew that your interval is not going anywhere. So you can go ahead and put in the 0, okay? All right, now I know that didn't really help. So let's go ahead and look at this equation here, right? So this is really 0 to pi over 6 of cosine 2 theta to the -3 power and sine of 2 theta, right? So in this case, you see that cosine 2 theta is to a -3 power. That's your more complicated power. So that should be your u. So your u is cosine of 2 theta. Let's take the derivative. The cosine is negative sine of 2 theta. Don't forget the 2 theta has a derivative of its own. So there's a 2 that comes out, a chain rule. Don't forget d theta. Move the -2 outside. -1/2 du is sine of 2 theta, d theta. Okay, again, more work. We're going to plug in the pi over 6 into this equation here. So u equals cosine of 2 times pi over 6. That's cosine of pi over 3. That gives me 1/2. U of 0 is cosine of 0. That is 1. I typically write the u of, so I know what I'm plugging in. So that makes it a little bit easier to follow. Okay, now I'm ready to go ahead and substitute. First thing I substitute is my interval. My interval changed from 0 to pi over 6 to 1 to 1/2. Again, the 1 came from the 0, so that stayed on the bottom. You don't move it just because the number is smaller or bigger, okay? And then I have cosine 2 theta to -3, so u to the -3 power. And then next one, sine of 2 theta d theta, sine of 2 theta d theta gets taken care of by -1/2 du. Again, quick check. Everything's in terms of u now. Beautiful. I can now take the antiderivative. I get -1/2 u to the -2 over -2, 1 to 1/2 up here. I can keep it as 1 to 1/2. I don't need to switch it back. Clean up your coefficients. So -1/2 times that -2 on the bottom gives me a positive 1/4. 1 over u squared, because that's -2, right? 1 to 1/2. So that's 1/4. 1 over 1/2 squared minus 1 over 1 squared. Okay. So you have 1 over 1/2 squared. 1/2 squared is 1/4. 1 over 1/4 is 4. 1 over 1 is 1. So your 4 minus 1 is 3. Your final answer is 3/4. And that's your final answer, right? So again, use substitution is supposed to make your equation easier to work with. Is the work itself easier? No, but it does make the equation, the integral, doable, okay? All right, quick break from use substitution, like really short break, just to remind you of what the exponential rules are. So when you're subtracting your exponents, you're really dividing. So this is really dy over dx equals e to the x over e to the y. Now this was in your practice in 7.1. Again, not a bad idea to kind of review. To separate your variables, you go ahead and cross multiply. So e to the y dy equals e to the x dx, right? And then now to get rid of those dy dx's, you simply take the integral. And to remind yourself, e to the x should be your favorite thing so far, because e to the x, the derivative is e to the x, hence your integral is also e to the x. So integral e to the y is e to the y. Integral e to the x is e to the x. Don't forget your plus c. Again, remember to remind yourself that the constant is only added to the independent variable side. All right, lastly, to get my y by itself, because when it says solve the equation means I want y equal, you simply take the natural log of both sides, right? So then your final answer would be, these two would reduce out, leaving your y here, your natural log of e to the x plus c, right? And that's it. That will be your final answer, okay? All right. So on the same thought here you have dy. I'm going to move the 4 root y to the left-hand side and then multiply the dx over to the right-hand side. So I get dy over 4 root y, because I'm dividing by both of those, equals natural log of x over x dx. Okay, yes, I know taking the antiderivative will help me, but before I officially take the antiderivative, I'm going to rewrite this so it's a little bit doable. So I rewrite this as 1/4 integral of y to negative 1/2 power dy, right? Any coefficient can go outside. And this right-hand side, I'm going to rewrite it as natural log of x times 1 over x dx. Okay. So why am I doing that? On the left-hand side, you can look at it, it is just simply power rule here. This is the y to negative 1/2. So you can use power rule there to go ahead and solve for that. You get 1/4 y to the positive 1/2 times the reciprocal of 2. But on the right-hand side, you have 2 x's here. There's a product there, so you have to use your u substitution. This is where I say when you have natural log, it trumps everything. Because you say u is natural log of x, therefore du, the derivative of natural log, is 1 over x dx. So this integral now becomes something doable. Instead of 2 x's, you now just have u du. So then you can go ahead and take the antiderivative and get u squared over 2 plus c, right? So I'm going to continue working my problem here. Cleaning up the left-hand side, I get 1/2 square root of y, because remember, I'm trying to solve for the initial value. I have y of e equals 1, so square root is actually a lot more useful for me. And then on the right-hand side, you have u squared over 2 plus c. Now, we're not going to use u. We've got to put it back in as natural log of x, because the initial value pertains to the x value, okay? All right, so now I see that I'm supposed to plug in e for x and 1 for y. So 1 here and e here. Okay, so that's 1/2 square root of 1 equals natural log of e squared over 2 plus c. Okay, as nasty as that looked, go ahead and remind yourself, 1/2 times square root of 1 is 1/2. Natural log of e, if you don't remember, remind yourself, natural log of e is 1. Natural log of 1 is 0. These are really good hints and reminders of natural log, right? So that's 1 squared is 1 over 2, 1/2 plus c. Hence, c equals 0. Beautiful. I got to plug that back in here to solve for y, because I'm trying to solve for the initial value equation. I want the equation. So 1/2 square root of y equals natural log of x squared over 2. Okay, I'm almost there. I want to get y by itself. Multiply both sides by 2. So that way I can get rid of the fractions here nicely. And I have root y equals natural log of x squared. So naturally, to get y by itself, you square both sides. So your final answer would be y equals natural log of x to the 4th power. Okay. Make sure you spend some time really understanding u substitution. It is a huge, huge part of chapter 7, and it's going to play a very important role in the next unit. Okay? All right, that's it.